Hey, welcome to Compiler Club. Here today to talk about compilers or Clifford's bad lawn care situation or crazy things going on at work, which is all process related on setting up a new project. Just stupid for process. Yeah, Clifford the Big Bad. Yeah, it is. Oh my God. Clifford the Big Bad Lawn. That's what it is. But maybe talk compilers instead. That would be fun. Type theory, implementation things, people talking about ref counting. Simon's not here to talk about ref counting glows. Fine. Everyone's been recorded. We show up on YouTube in a couple hours. I don't know what happened last week with the video. There's not like I have any options about how I upload the video, so I don't know how YouTube got the wrong one. It's fixed. Hopefully we'll get the correct one next go round. Um, The other trees and leaves, yes. There were no leaves involved here. I guess there was poison oak leaves, so maybe there were leaves. Yeah, there were. Yeah, fine. And I took the garbage out in that sense. Or at least I let it be collected by the local outdoor collector, which will be, the birds and the bees and the bugs and things. Um, yeah, whatever we want to go here. I talked with somebody about doing the correlations between abstract syntax trees and sea of nodes on and off last week. And then the last meeting we ended on a note, somebody had a question. They're going to ask something.
Yeah,
Yeah,
I was asking something about aliasing, but I forgot what it was.
me too.
Oh, I think it was. I asked, like in C, you have a restrict keyword and how aliasing works in C. No, it was not a question. It was something that came up afterwards. I'm not sure what the original question was. Yeah.
Yeah, no problem. Yeah, the AST correlation was just you can treat it like it's another version of a graph and do people optimizations, which people with ASTs for the dawn of time. But this is exactly what's going on in CF nodes, except the graph's a little more complicated. And then that's it. And then there's just like, oh, look at this. So some young compiler guy discovered correlations on doing graphs. Um,
I've got a question about that. I wrote in a blog post like yesterday or the day before that Sea of Nodes uh, defs point to uses. I kind of said that unequivocally. I don't know if that's true in all implementations or just some or optional or some of the time.
I do uses point at defs for me as a
Yeah,
single raw pointer because that's your semantics. If I'm adding A and B, the add needs the A and the B, so the add points to the A and the B. They're
yeah.
ordered because A minus B is not B minus A. Fine. Fast optimization wants me to go the other direction as well. So I have them pointing both directions as raw pointers. The one direction is sorted, the other direction is just a list, essentially done as an array list that's embedded in the node for me, however people want to do that.
So is that C2 and simple, or do you know offhand if like V8 Turbofan does that or
It's C2 and simple. It's me doing implementations. I know other
yeah.
people have done that as well. Again, they've admitted more or less copying me. There have been the V8 guys did their own thing, and I don't know if they went down that path. I know they did the effects very differently, and they did a bunch of things with control very differently that I think didn't do themselves any favors. I think they shot themselves in the foot there. Um,
Well, that's another
but I don't
interesting thing.
know.
It's like dynamic language stuff with Sea of Nodes. I feel like you kind of have to go into Sea of Nodes after speculation, otherwise you're just screwed.
I no, I hear you. I don't believe that's true. I'll claim that Hotspot essentially does tons of speculation, and I just inflate the nodes for in speculation as I go. Um, we could argue left or right on this. Like
Well,
all
for the
the safety checks and all the we think it's this, but maybe it's that things all got jammed in early in Sea of Nodes. And then the huge numbers of redundant checks get cleaned out and the specialization just gets cleaned out as you change how where you merging and whatever. There's this transform I do in CF nodes called unzipping. There's a moral equivalent in any language. It's not specific, but it just says I have a thing that I know, and then I split, I do something special, and I do something generic, and then I merge. And I forgot that I knew something. And then I discovered it again, and I split and I merge, and I split and I merge, and split and I merge, rediscovering every time. And the unzip for me is this is a zipper, and I'm unzipping by making it two parallel lines. I know it, and then over here we always know it, and over here I never know it. And then this path usually gets chopped off and sent off to the slow path. Don't be fast here.
I get
Um,
suspicious of the V8 stuff mainly because like I don't know if SSA-CFG would actually change the like underlying issue as much as it like just gave them more educational material on the stuff, so they just like knew what to do that way. Like it's not like Sea of Nodes was the limiting factor. It's that education around how to use it is probably just really hard. Like the knowledge transfer is probably just really
right.
difficult.
Yeah, I really wish they had come talk to me when they started in on that path. I'd have been happy to at least tell them what I did and why I did it, because they went
Yeah,
down a path, like I said, that I would never have gone.
yeah.
Um, the effects things I've just always treated as values in the sea of nodes, all possible effects, including IO effects, or in their case, I think I know what an object looks like until somebody adds a new field in. That would just be another flavor of an effect.
Yeah.
Um,
The one I remember getting picky about that came up was the load elimination stuff because there's two ways to approach doing that, like two main ways, and they didn't do either of those. So like there's the Cliff, it describes one route, which is basically you write these peepholes that can look up some arbitrary distance, and then you like you can fold in that way. And so you have like well, like a peephole, you have a sliding window basically. The other route that I've described is basically just a port of the way that people do load elimination in CFGs, which is just that if you look at your memory nodes, you have a CFG. Like you can look at it and say, oh, anytime that a memory node, any memory producing node has two users, then that's a fork. If you have a phi, then that's a join. And you can have phis that loop back into themselves, that's a loop. And so you could think of a phi like a region. And in which case you could just walk your CFG and then do it as if you were using a normal CFG. And it all works out. Um, it actually, the neat thing is that there are certain things that pop up logically there that don't pop up with a normal CFG. So one of them is that you could have a fork within what is in a CFG the same block, but logically they're two separate like parallel sets of effects. Because in CF nodes you can split memory arbitrarily.
Throw this down in the docs as a piece of code because your hand waving isn't doing me
Yeah,
enough
let
good
me see if
here.
I can. Yeah.
Well, I'm not here to sort of crap on V8, but I'm here as another dynamic language person, just saying like if every opcode is a send, you until you've injected your all of your like fully specialized or strength reduced or whatever, like everything is maximally effectful until you just
Yeah.
just crapped in a ton of guards, and then only then does it make any sense to split memory because you
Yeah.
just can't before, like you don't know what's writing to what. And I
Yes.
think that's challenging,
Okay.
especially if you go straight into Sea of Nodes, right? If you go
That's what
straight
I,
into Sea of Nodes,
okay. I'll only ever do it that way. Go straight into sea of nodes and then start doing your analysis and then begin inlining your guards and inlining your decision points. This inlining basically clones some more code in and it works out fine. It's one of these things where I get to a really simple IR. It's the only IR. Everything else is just going to be pieces of it. That IR does everything, but it's really powerful as well as being really simple. And part of being powerful is being really simple. And so if you have this thing in your head where I have some sort of fun, special, weird semantics and I want to specialize to make life better, what happens in your implementation if you weren't doing code gen and you were just executing it in an interpreter? You had a test at runtime that said, I added a field or I didn't add a field or I did whatever, I changed the shape or I didn't. Okay, now you're generating code with that test in. Well, generate the code for it. When I first started doing Java hotspot, everyone thought I was crazy to put the null pointer checks in the IR directly for the safety, bytecodes. Well, just put in an IR piece that has, here's the bytecode piece, but that hid the safety check inside of it. I could have done that, and I said, no, put the safety check out as an explicit part. Oh, here's another safety check, and another. This giant redundant piles of safety checks. Isn't this slow? No, in fact, the second one that comes in does a peephole immediately from the first one, says, I'm redundant, and he folds up. And he folds up in your L1 cache, and he never actually consumes any memory, and he just disappears as you go. And then the parser is a little bit smarter, so he does more even more aggressive earlier. But the general theory is the core basic optimizer running as you build the IR in the first place cleans up the crap from the bazillion specializations and safety checks you need just right as you do it. And before you walk off the end of the parser, you have got an IR that's been specialized for the obvious common cases already.
So
And
that's actually kind of what they're doing in Maglev, I think. If I'm reading their builder correctly, it's just not in a sea of nodes, it's in the CFG.
That's the main thing that I've come to, which is that it's it's like a knowledge transfer thing, because a lot of these things can just be applied to like sea of nodes. Like the complaint of, oh well, if we can't specialize, then like that might bloat up our graph. It's like, well, that's true of like the CFG too. Like the if statements are all still there and the calls are all still there, and you still can't split memory. Which, to be clear, you can in fact implement a memory SSA in CFGs. It's just that people rarely ever do, or they just make it a secondary source of truth, which makes it even worse, which is like the LLVM route, where you say, well, sometimes we'll step into memory SSA, but because we're not always in memory SSA, that means that you can't rely on it. Sometimes you'll have to just throw that information away and just go, well, it's gotten outdated because some pass didn't preserve it. If you just always preserve it, then it's a lot easier, and you could just be conservative with it. You just don't have to split memory if you don't know. And so if the V8 graph comes out the first pass and you don't know that much about the types because you haven't done enough profiling, you haven't seen what's going on, you could just start off with the most conservative, all of memory. And then you could say, hey, I've got this new allocation. I know that it's a new allocation, meaning that I can split memory here up until the point where I know that it escapes and I can no longer track its aliasing.
Yep. I'm doing that right now in simple. Yeah, C2 does it too. Simple, maybe a little easier to track. Exactly. Hey, it's a new allocation. It cannot alias. Therefore, it does not. In fact, I do that in the parser directly, just as I spit things out, because aliasings, you have textually obvious in the parser. So, yeah, you can do all this stuff just straight as it comes out of the parser and fold it up as it goes, including inlining.
Like
I am happy to inline in the part while I'm parsing.
So a lot of these things, I'm not trying to pick a fight here.
No, pick
a
a
lot
fight,
of these
please.
things
Makes for
get
better.
a little bit hand waved over. And so for example, Ruby, you have opcodes coming in that look like point.new gets emitted as a method send to some object. You don't know anything about the object. If you inline the new, you see it's a call to, most of the time, initialize, and then you can maybe inline the call to initialize, and only then does anything writing to this object actually see that the object new opcode, the object new IR node, which is the thing that doesn't alias anything else. So it's like only after 2 levels of inlining, which is you maybe could do in the parser or maybe not or whatever, but it's like it's rough out there for if you don't have like an allocate opcode.
This is what the pushback I got when I was doing null pointer elimination in C2. Exactly. You can't do that. That's just too much. It's rough out there.
I'm not saying can't. I'm saying hand waving blah 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 in the parser. If you're doing 2 levels of inlining in the parser, I think, wow, that's amazing. I don't want to do that.
I think C2 did all of its inlining in the parser, basically.
Yes. 100%. Not that that's the right answer, but that's what C2 design came in for other unrelated bad reasons. So where I'm at right now is that I emit some IR from the parser. He reads your source text and produces something. Okay, fine. And then he just runs till the peephole list runs dry. And then he goes and parses some more. Okay, somewhere along the way, it comes a function call. Do I inline it or not? I ask the standard heuristics that everyone asks. Is it small? Is it hot? Is it common? Is it blah, blah, blah? Okay. Does it make sense to inline it right now or delay? Sometimes I just inline right now. Sometimes I'll delay. Later, when I've got more stuff around and I've done maybe frequency analysis or loops or something like that, I'll go make a different decision to go inline. This seems all are pessimistically okay, and you just add more IR by inlining until you decide you've got the optimal set and you quit. The fact that you did it in the parser or you did it later makes no difference, at
Well,
least
that's actually
for
the
CF
other
nodes.
The other
But
the other
the
distinction
reason
is
you
that
get away
like
with
nothing
just
really changed.
Okay, so we have
Go
three
ahead.
people who want to. Arthur hasn't spoken in a while, so it was. Or no, it was Aaron. Maybe go first.
is the reason you're getting away with that because you have bailout paths that you just put a bunch of code checks in the logic. But if those checks fail, you essentially have to either bail to an interpreter or recompile the whole function, assuming that
Right? No,
your
it is
shape has
not.
changed.
It is not why I'm getting away with it. That is a highly useful behavioral effect that says I don't need to spend a lot of effort compiling super optimal slow path. But it's not the reason I get away with it. The reason I get away with it is because at every point while I'm parsing, I have a perfectly correct graph that has the full program semantics available to me. So when I come to a point and I'm mid-parse, I just stop and look at the graph. As the graph stands right now,
So it
can I
basically
do
doesn't
something
matter
with
that
it?
any function call can do anything because not every function call does do anything.
I missed the lead in there. Say it again. And then Max is
With
raising
things
his
like
hand.
Ruby, you get into a lot of pain because any function call can
Yeah.
do anything.
Yeah.
I set a value, but that value setter could have been a function which could have mutated the shape of the object.
So if you
And you're
have,
just saying it doesn't matter that they can do anything because they don't.
yes, yes. Given the text you wrote said a variable equals val, the semantics are function call to a putter, then the IR gets a function call to a putter. Okay, now that you've got a function call in your IR right in the middle of the parser, ask the question, is this putter trivial? Is it time to inline it? Maybe it is. These are all like 5, 10 clock cycle questions to go ask on a pre-cooked putter, the standard default one that does nothing. You'll ask in handfuls of clock cycles. I'm a trivial putter. I have nothing to do, so inline me. Okay. For this kind of a thing, the inline again is a dozen opcodes come in for call head tail. You'd optimize for putters that are default, but the unoptimized version is just some amount of call nodes wrapping, and then the peephole says clone the tiny body. Oh, it's one instruction. Okay, done. And then it folds in and it disappears. And these things all can disappear in your L1 cache in microseconds, less. This is like easy stuff to do in the common case where you're not doing anything weird. But you put in the general case in the IR, and then let the optimizer decide that the general case was actually the common case and there's a hot path and you can take it. So from there, I'm going to go down chat order, which would be Max. How do you split profiling info?
So
Yeah.
there's we're doing an inliner now, and yay, we do the graph transformation easy. We profile in the interpreter, and that means that sometimes you'll have a method that's polymorphic or megamorphic or something disgusting, but the caller is perfectly monomorphic. And we've seen a couple different runtimes do different things. JavaScript core inlines bytecode, so you get call context that way, and then it does compile later. SpiderMonkey does this thing where they pass down the interpreter writes its profiles in a one call context specialized scratch area, and that's how you do it. I don't know what C1 does to collect profiles for C2, but like how does C2 handle profile splitting for like for that situation?
Yeah. So C1 makes its own inline decisions and has separate profiles on all its paths that he inlined. C2 forces the inlining decisions that C1 has. It takes the identical ones plus more. He may inline more, but he does at least what C1 does. And then he takes those specialized profiles and slaps them in his own inline variations of it.
Okay, so there's already call context in the
Yes, from
profiles.
C1 did some amount of inlining. C1's inlining is quite trivial, but it's enough that you get some specialization. And then C2 honors that, takes that directly.
I don't want to write another tier yet.
Well, it's just two, for me at least, or three. There's the interpreter, which only counts back edges and calls. That's it. C1 takes that, does some inlining, and puts counters. And once you're in C1, the cost to count drops by tenfold. It's super cheap to count now.
Oh, I'm talking.
Two says
I'm talking
whatever
about, like,
tiling of inlining you did, I'll take, plus maybe more. And
I'm
then
talking about,
I'll
like, value
I'll
profiling.
keep the ratios on whatever call path. I have some frequencies here, and I split, and I took the same inlines from C1 twice. I'll just keep the same ratios internally.
Does that do value profiling by, like, oh, this class here and that class there, and
Yeah.
okay.
Oh, absolutely. That's a big one. If C1, if the interpreter said I only had one guy here, which he'll do, but that's kind of his limits. He says he got called, but you can look at the counts and say, no one ever called this one. Somebody called that one. Okay, that's your profile. Then C1 will do that for sure, and you get even more counts, and then C2 will totally honor that, and yeah, you'll get the hot path. I'll just go ahead and check that it's this. Okay, else cut it off. Go back to the interpreter. Profile again. Does that answer where you're headed here?
Yeah, we have to figure out how to do call context without getting another tier. I think we're probably going to go the spider. I don't want to inline bytecode.
Well, what are you doing?
What do you mean? What are we doing? We have a
who are
JIT,
you? You're Max. What are you
I'm
doing?
Max. Oh, we have a new Ruby method JIT.
Okay, we are Ruby.
Shopify. I'm at Shopify now.
You're at Shopify doing a Ruby implementation, and you're
Yeah.
targeting JavaScript or Java.
No. I'm when you bring up a new JIT, there's like 40 years of research, so you beg, borrow, and steal.
Yeah.
And that means I'm reading all the code bases. So it's just Ruby. It's
Okay.
Ruby JIT and Rust, but the the same stuff applies. So it's like, where are we getting the call context from? It sounds like we're going to have to do something like SpiderMonkey does.
You said, I don't want to add another tier compilation, but that says that you have two and you want to add a third.
We have an interpreter and we have a C1.5.
Gotcha. Yes. And now you have this tough call. Yeah. Okay.
One option, I'm actually really curious about the Ruby stuff for a few reasons. One of them was the thing you mentioned about inlining earlier, but then also I lost my train of thought. There was what did we just say? We just said Ruby. There was something else.
Splitting?
Oh yeah, the different compilers or the different tiers. One option is just to like flick off a bunch of settings on the same compiler. Is that what the 1.5 does?
No, I'm saying, like, our current method JIT is like kind of it does mostly C1, but some stuff we're going to do some stuff that approaches like IGVN kind of thing which we could just turn off, right? But the there's still like lag. Like, I don't want to have even with a really fast compiler, if we just made a decision and went through our pipeline and then we left it alone, that's still more latency than we want, compile latency than we want in like for application boot. So I'm trying to figure out, I mean, it's just like
you're talking about turn off. What you mean was the two tiers are my old tier with something disabled, so it's faster, and the same old code with everything turned on. Yeah. I know Hotspot went down that path for a while. There was a C2 cut down and a C2 full. At Azul, I made C1 and C2 play nice together, and I ended that way. I don't know where Hotspot is now.
They have like, I think it's like 2 levels per compiler at least, or something like that. So I don't know what the tiers exactly mean, but it's like you get like C1 the first version, then you get C1 the next version with a little bit more info, and then you get C2, and then you get like the fullest C2 with the most stats. I think it's like a stats
5 levels.
Yeah, they have a lot of tiers.
It's basically C1 and C2, but in C1 you have different levels of profiling, and sometimes they use non-profiling C1 as a fallback. For example, if C2 compile queue is full.
Okay, that's
interesting. Like 4 or 5. I'm seeing 5 here: interpreter, no profiling, limited profiling, Yeah, so okay, so there's one C2 tier, and then there's 3 C1 tiers.
3 C1 tiers.
Yeah, it's just like no
It's just
profiling,
different
limited
levels of
profiling,
profiling.
and then full
Yeah.
profiling.
Wow. Okay. That's interesting. I walked away a while ago, so this is all news to me. Interesting.
The I posted in the doc the thing I was talking about before with the memory nodes. Yeah, hopefully
Yeah,
this
okay.
example like clarifies what I
Oh,
mean.
okay. Yeah, and there's a bunch of people in the chat have questions. So let me pivot through those, and then we'll pivot back to what you're writing in the docs.
Gotcha.
Ben, you said doesn't matter when you make the inlining decision, so long as it's the same decision every time. If you inline later, do you do? Um, what I've done in simple is say I have this one-step church roster property, so it doesn't matter what order I visit the work list, all things end up in the same exact point every time. You get the same identical IR, and that will be true up until you increase code where some non-monotonic behavior can happen, where adding code causes you to discover something with a sharper analysis that lets you delete more things. So there is a decision point to be made anytime that you would add code that can vary if you don't force everyone to add that particular inline every time. So if the inline is too big to take it by default, you want to know something about inlining it, then you have this issue where it could be that inline decision versus a different one. If I had two equally interesting inlining decisions, then neither one's going to fire automatically because they're just too big. So I picked one first. It could prove some interesting optimization that deletes the entire second code path and says that code's dead, it'll never fire, or not, or vice versa, does something worse the other way. So there's some non-monotonic behavior when you add code, which sharpens your analysis that lets you do other things. Otherwise, it would be perfectly the same, and it would be semantically provable, it'd be mathematically provable. It didn't matter what order you did them in, other than performance, it all come out the same. Compile time, it all come out the same. No, it's not true. You can get a difference, so you have to pay attention when you inline. Fine. Ryan wants to talk about a new topic related to inlining, and Matt is bemoaning that we don't have Java amounts of time for application boot. Yeah, Java's pretty quick, but it's not as quick as JavaScript, and maybe Ruby's in there. Okay. Yes, and the inlining small methods, C simple and C1 or C2 for that matter. If the method falls below some small size threshold, it's 100% inline. It doesn't matter when or where, other than if you do it early and it provides knowledge like it does a null check that then bails out if your null is just dies, then everyone afterwards can say, oh, we know it's not null already because you've inlined this null check right away. And getters and setters and a couple other trivial things, including people who check null right away, do get inline in C2. Simple has a different, dumber heuristic, but same theory. So let me go and grab in order. I think Ryan's topic about inlining would be no, Yasser's topic beats Ryan's only because that was the order it came in. I don't care. But we'll come around to Ryan. You're coming up. Let me find the share on the docs because that's where Yasser said something about examples.
Yeah. So this example I've just got like stores memories, and this is just like a crude C what's it called, like C of nodes thing.
Yeah.
Technically there's nothing really unique about it that makes it like C of nodes. You could put this in a basic blocks, and the trick is that with these nodes by themselves, you can already see the outlines of the basic blocks necessary to do the load elimination. So for instance, we look over it, we start at the top, we start at the projection at the top because that's the root. And then we just have to look at, there's two types of memory nodes, basically. There's either the kinds that produce things or the kinds that consume things. The kind that produce also consume, but yeah. And so, yeah, so Cliff wrote down like, oh, there's a merge point there. It's like,
Which
well,
means
we
there's a
see that
split
there's
point
two coming
here.
in. Yeah.
And I'm going to indent you to be like as if I'm inside the loop and it's two different basic blocks in the split.
Exactly. Yeah, you can sort of see that like there's basically an if else going on there. And so what I would have to do is, if I wanted to do the load elimination the sort of traditional way, is I would look at every basic block, walk to every memory writer, and then track what the latest version of the write is in my cache. And then if I run into any like writes that, for instance, I don't know the aliasing of, I'm going to have to just throw away the entire cache because I can't see past it. I mean, unless I guarantee that something is like beyond the cache, so like, oh, this thing doesn't alias with anything, but it obviously can't alias with immutable values, for instance. So we could just say like, well, those can stay. Other than that, anything that it could a write could potentially alias with, it might just clobber that. And as long as we do that, we get like this what would you say, like this cache of the latest loads of things. And the way that we do that is we just keep walking them basic block by instruction by instruction. But the interesting thing you start to notice is that there's only two types of instructions we ever need to walk in the basic block to do that. It's either consumers or producers.
Yeah.
Producers change the table, the cache, and then consumers will read from the cache and see if they have a latest answer, and in which case they'll just replace themselves. Where do we find all the consumers in the sea of nodes, and what times do we find them? Well, there's an easy answer for that. Where do we find the consumers? They're always connected to a producer, because the consumers are going to be things like a load. A load has a memory input. Its latest memory input is what we need to check. So for every memory consumer, every producer that we stick to, let's say, I'll write an example here. So
can I throw in an observation? I'm going to there is a control flow graph embedded in the sea of nodes. The memory edges typically are a subset of the CFG because you can't afford to have a clone of the giant wad of all of memory. So your serialized memory all the time, it remains normally serialized. Therefore, it comes and goes only in and around. I mean, it follows the control flow graph directly, except where you have multiple memops within it, like a single basic block. So it's a subset of the CFG, if you will.
Yeah, you could also end up in cases where, like, if a loop doesn't do any memory operations, then the subset of the CFG that memory represents won't see the loop at all.
Won't see the loop at all, right?
Yeah, that's okay though, because we're doing load elimination, so we actually only care about the subset of the CFG that touches memory.
Yeah.
And so what we do is we go up to the producer, we do the caching thing where we fix up the cache, and then we take the users of that producer, the direct users, which is going to be some set.
Are you still stepping through how you do this in a classical IR?
So this is the part where I'd this is the part where it becomes like there's like an isomorphism where you could see how you could do it in both. I'll walk through the traditional case. So we've got
you're doing the isomorphism between the traditional case and the sea of nodes.
Yeah. It's doing the it's
okay.
doing emojis for me, but here. So this is where I'm at. You can see the cursor. Cool. So you've got this load, and all you have to do is when you're walking through the basic block, whenever you fork, you clone your cache, and you just say like, "Hey, this path gets this version, this path gets that version," and then so you have some version of the cache, and it's gotten updated to keep track of whatever A has. So like A is the latest version of whatever address is, and so over here, when we look at the cache, we see that, and we know that we just have to take whatever's at ... and we use that as our value now. And that's what we were doing at SSA-CFG. So we just walk the stores down until we see any loads, and then we just use those. In the Sea of Nodes version, you do basically the exact same thing, which is that you walk to the producer, you look at its direct users. Hey, are any of the memory inputs of this thing a load? If they're a load, then we do the caching mechanism. And then once we've done all those for the producer, then we move to the next producer.
Yeah,
and then sometimes we might fork and we might join.
This is not what I actually do, because I do something that's a little easier.
Yeah,
I
don't
walk anything.
have the people option, but this is the sort of traditional like memory or like the traditional
walk all and do a memory opt.
Yeah.
Yeah, okay. So I have the go walk it all and do anything, including memory ops, but anything else. When you visit the load, not the store, you ask the question, Mr. Load, how do you feel about yourself? Can you clean yourself up? And he says, well, my input comes from a store. My address comes from the same store. I therefore must be a load after store. So I'll just turn myself into the store's byte, right? It's the same thing. It's just that the load,
it's like a reverse version.
The load is the trigger or the root of the test.
Yeah. The one of the caveats that comes up. So in the V8 version, this is where you get like a mixture of both versions of it, and this is where the dilemma comes from, and this is where my prescription comes in. Well, I've got a few prescriptions of how to do Sea of Nodes because I've just been doing it for a while. And it's just become a thing. But one of these prescriptions, that the way that they do it is you have one of these monotone frameworks, but what is the value that's in the lattice? And the value is this like table of cache, like of cached values from previous things. But that means that every single store and every single every single memory producer can at the same time have their own individually allocated tables, but there's no limit on the size of the tables. So if you had a row of 1,000 stores, every single one of them would get a clone of the table at the same time that is a little bit bigger than the last one.
Get an n-squared growth in the table size.
Yes. And so that's why their thing goes quadratic. In this setup with the basic blocks, the neat thing is that it only scales with the with the number of basic blocks we have, because we only clone whenever we have 2 basic blocks. So if there's a stream of like if we have a row of a bunch of stores, what we could say is just take the same cache and keep mutating it over and over again, but it's the same table. We're just passing it along. And then whenever we reach a forking point, then we clone it, and cool, now we have 2 tables. Whenever we join, we can then delete one. And so boom, we're keeping memory usage significantly lower. And that's what they do in their Maglev version. They just don't do that for the, the old version, the turbofan version.
Turbofan.
Yeah. And so that's why the turbofan version is significantly more quadratic. It's like, well, it's doing a lot of memory cloning because every single time it has to, and it also, because it's doing it as a monotone framework, it is doing it arbitrarily ordered. So a node might not have its inputs ready because it needs to prepare the cache before it can do it. So like a store needs to have its previous store have prepared a cache, and it needs to allocate memory for that and then add 1 extra store to it. And it's like, well, that's a lot of memory, and that adds up really, really quickly. And so if you cut that down, you get drastically better answers, and you can do the algorithm that they want to do in Sea of Nodes without sacrificing anything.
Okay, I'm not figuring out where their algorithm buys them anything over Sea of Nodes. You're saying you can do it in Sea of Nodes without cost. I'm not sure what they're getting at all.
Yeah, I'm saying you could do the Maglev version of the algorithm in Sea of Nodes. The reason I get picky about this example is because they talk about it in the article as if Sea of Nodes made them do it this way. And it's like, well, no, the ordering thing is like, you don't have to walk in an arbitrary order. There is an order to the memory nodes. They're not arbitrary. They have a serialization, and when they fork, there's something to be said about the forks, and when they join, there's something to be said about the joins.
So this is the old article that I went back and forth with somebody?
Yes. I meant to do a video about this because I had built a version of this, and then I just like procrastinated, and then so I never made the video, but I'll eventually make the video because I should explain this with diagrams.
Yes, it needs some diagrams, but yes, they like I said, they shot themselves in the foot a couple times, and then they tried to blame me for shooting themselves in the foot too, which I didn't appreciate. Fine.
There's one last thing.
It's like, let's not wail on them. It's just like move on.
Yeah. It's less about trying to like do that. It's mainly about trying to like make sure that somebody understands how the algorithm can be written to not be inefficient.
Yes. Okay. Yeah. I didn't understand how they got to their inefficient place in the first place. I didn't, but I'm too far into the path here. I'm like, it's obvious to me what the hell's going on, why it's going on. And then somebody else comes along and says, here's a different implementation and it's really bad. And so you suck. And I'm like, why did you Twitch do it that way?
I see what the wrong path is. And I think I think it might be something to point out in other Sea of Nodes education stuff, which is that there are algorithms that are not just monotone frameworks that do just randomly grab nodes and just arbitrarily do things to them. There are a lot of passes that do that, and it's really useful. Whether that's like constant propagation or the p-poles and things like that. But there's also things like vectorization that might say, hey, I want to do this in an ordered fashion. It might not even be a fully ordered fashion. It might be like partially ordered. Like, hey, we know that this like trace is, it's got like no loops in it. And so we treat this as like one trace or something. I was like, okay, cool. I think that the distinction of when to do either is not something that was like picked up on by whoever wrote the original algorithm. And so you ended up with a situation where they kept making these monotone frameworks that had arbitrarily sized allocations, and they would have it would have benefited from a better like a stricter ordering, which is what I'm advocating for here, basically.
Okay. I mean, okay, fine. Like, I mean, for me, this kind of stuff, it's all constant size, linear time, constant times linear is linear.
Yeah.
So I don't. It doesn't matter what order you visit then, as long as you visit a neighbor when you change a neighbor, you're guaranteed linear and run to
But that's true as long as you're not doing something where you might say, like, that's true because the p-poles you're doing are taking a node and producing a node or even just taking a node and like recycling an old node. So they're especially like not
There's
producing new
that
nodes.
piece for the peepholes, but there's hand in hand is the monotone analysis framework I'm using that just carries values forward, right?
Yeah. But
Right.
if the values were scaled with the size of the previous value,
Yeah,
then
no, that would
this
be
wouldn't
bad.
work.
Yeah,
Yes.
that would be bad.
And that's the distinction like that.
That's what
I
they
think that was the
did
flaw.
themselves with. Yeah.
Yeah.
I get that. I fine. Yeah. Okay.
Yeah, and then a minor comment for Max earlier. He mentioned the case of the inlining stuff, and I wanted to hopefully provide a little tip with that, which is that you mentioned like, oh, well, we might have these cases where we don't know like that there's an allocation because it's like hidden 2 layers deep. One of the things you could also do is have like method level escape analysis, because there's a lot of functions that are like these constructor, like fake constructor thingies where they create a value and then they just pass it along.
Yep.
And if you could just tell the caller, hey, this guy is just passing you a newly allocated thing, like he allocated it. Or maybe he didn't allocate it, but he got it from somebody else who did allocate it. And so you're just passing along that ownership information. And then that
Factories
way
are
you could do the
really
aliasing.
common, and you want to really optimize for factories. Yes.
Yeah.
However that's done.
Yeah, which could be done with inlining, but this is a way to do it without even triggering the inlining. You could just say, hey, well, I know that it's going to be escaping, or it's not going to be escaping.
I have it in simple now without inlining to manage the escape things through by declaring that the memory that comes from this call includes from the constructor includes a chunk of private memory as one of his output results. There's a private pointer pointing to private memory, and here's the private unaliased memory. So he produces a private memory state along with the normal public memory state. I did global plus plus on some unique ID counter. I did. There's a global update too, but there's a private update and a private memory field. And that remains private until it gets escaped, which will happen as soon as you're done with constructor. And then if you inline, you could preserve the didn't escape past the constructor. But I keep it private at least through whatever nested stack of constructors you have.
Yeah.
We would just
that
need
won't solve all cases, but some.
We would need method splitting, like as a primitive there
Yeah,
to make that work.
And when I say inline, it's effectively a method split.
No. But Yasser was talking about the non-inlining version. It's like if we don't inline, then we need to have code splitting. I don't want to.
Yeah.
It's
to be fair, if the function's like big enough and like it starts getting messy, you could probably just write it off. But like this will at least catch the factory cases that you see everywhere.
Yeah. We thankfully, I think mostly the pattern is capital whatever dot new, and that's just object dot new. So we know that, and we specialize that, and we see through that to initialize, and initialize normally is like no more than 20 opcodes. So we just inline that, and then we see basically alloc, right.
Yeah.
People doing whatever they're doing, and then we can do load elimination. We can do whatever on that, and then it's happy. You just have to inline twice. I mean, actually, the first one's not even a real inline. The first one is we see that it's we're specializing the C, we're intrinsifying the C call that does an uncached lookup and call of the initialize, and it's like we just fake it in the IR. So we inline it, whatever.
You're inlining it effectively early. Totally reasonable, especially if your IR has particular patterns that repeat over and over again. Absolutely.
Yeah. It's like that and lazy initialization, all this other stuff that we got to just figure out how to handle nicely.
Okay.
Yeah, but the factory case without inlining, I don't think it buys you much if you still cannot eliminate the allocation. Like you get some properties for aliasing, but not too much.
No, right. And then my goal for that is to inline it down to where I can get rid of the object allocation. Yes.
Mm-hmm.
Right.
We have a nice little benchmark.
The privateness didn't save me. It was the reason the privateness was there is so I could determine that the object did not escape, so I could get rid of the allocation. Yeah.
We have a benchmark that's like allocate a point, allocate another point, like add them to, or no, check equality. And so the whole thing there is like, can you inline everything, do the see the stores, see through the stores, see through the loads, oh, they're all equal, and then just delete everything. That's like the litmus test there is, can we just completely
Yeah.
erase that to true? That's the easy case, because if we can fold it to true, all of the speculation goes away. That's not true. Some of the speculation goes away, but then the harder part is like pushing the reconstruction into the guards, or like
The slow path.
the slow paths, because you can just read. I mean, it's the same thing as like class loading, but worse. You can just redefine anything at any time. So we have to handle the case where someone redefines any random method involved,
C2
and
has a
we just have to push the.
C2 strategy. There's the safe point, bailout, exit path. It takes all of the live inputs that are just regular Java pointer values, primitives, whatever. And then when you've gone to the path of I've delayed an allocation, he'll actually push the allocation down that path. And at this point, I think I split from what Oracle was doing, Sun was doing, and had it be I generated the code on the slow path to do the allocation, and I think Oracle said we'll generate a table entry that if you unpack on this direction, will allocate it in the runtime as opposed to in the generated code. But there's some cleanup path that says I have to go make you escape the object. In the end, I have to go make the object wherever that piece is.
The problem with allocating in the compiled code is that if you need this allocation as part of the state of, let's say, a GC safe point,
Right.
Do you have a place, like, do you have I don't know, a place where you can generate the code, and then your runtime needs to, I don't know how to
I had the
wire
place
this piece
to
of code?
generate it because I just put the code in. It's the if that allocation fails, what do I go on what do I put in for the machine state, the Java architected machine state on the out of memory error? What
No,
are
no,
your
what I'm
side
talking about.
effects?
So let's say you have an allocation that is unescaped and removable, but then this allocation is used in a deopt state for a GC safe point poll.
Right.
Uh, if it was an uncommon trap, you would have explicitly the code path where you could sync the allocation. But for a safe point poll or just deopt state of an arbitrary call, you don't have the dedicated code path that you execute before it. So you need to have some kind of interaction with runtime, either symbolically encode the allocation
Oh,
or
no, I'm trying to remember what I did at Azul. I'm pretty sure I gave you a test that said you're going to take this slow path code here as a long latency branch from the fail allocation. You're saying you stop at an arbitrary safe point, then you blow. The arbitrary safe point has a pointer off. Go run this code over here. He's going to fix you up, including allocating what you needed to allocate to bring you back to the Java machine state, which is different, I believe, than what Oracle ended up doing, which was more like what you're saying.
okay.
There's some table
So
entry.
you have basically arbitrary code you can execute if you take a deopt from
You took a
arbitrary
DOP,
safe point.
you ran this chunk of code over here. Yeah. And
Yeah, I think we considered both. We are doing this symbolic description on the side, and basically we have a DSL that we run in the deopt handler.
yeah.
It is a bit more compact than just generating the code, and there are a lot of deopt states in
Yeah.
the code. So
I think that's entirely reasonable. I did what I did because it was the fastest path to get job done, but it was slow path, so I didn't really care too much about it. It did bloat the code because you had all these little bailout snippets. Yeah. Um, I think Ryan was like trying to say something about LLVM and inlining an hour ago.
Yeah, so I was thinking as far as like strategies for like building with LLVM, my thought was like, so I have obviously like many like graph nodes, right? Different than your sea of nodes, but um one of the problems that I might encounter here is that LLVM is like, it's kind of single-threaded from what I understand. So if I want to like optimize something, I probably have to optimize it kind of in isolation. So I was thinking, what if I compile each function, but start like instead of like directly compiling every function together. So I take a function and then I say, okay, I'm going to look at a certain depth, maybe 4 layers deep or something, or a maximum, like maybe I keep recursing until I have a maximum of like 16 functions or something. I don't know. And then I make those available for inlining, and then I compile that one function in isolation, and then link all that together at the end. Like, would that be a good strategy, or should I just bite the bullet and just throw everything together and then compile it normally?
I'll give you the worrying answer, which is that, or I'll give you the worrying and really probably 99% case. There's a bunch of functions that are like leafs that should basically always be inlined that might appear in a different bundle than something else. So you might want to duplicate that into each one of the bundles or inline it manually. So like, for instance, let's say there's a hash function that's like pretty simple, but shows up all the time in different files. This hash function's either going to end up in, like, if it's only allowed to end up in one bundle, then it might end up in one of the bundles out of, let's say, 20. And so you might miss out on things like that. Another option is just putting it in all 20 of the bundles. The other option is just trying to grow the, what's it called? So instead of it being like, the other option is trying to figure out ways to group the bundles to account for this. So like if you go like top down, then you might end up missing this because you might go like, oh, I grab from this class, and then this class has some calls, and then those calls get some leaves. But then there's like this separate class that's not in the same, like, top-down view. But if we started bottom up from this really common leaf function, we might be able to say, oh, there's like 20 callers of me. Let's put those all in the same bundle. And then you've like, but all those choices end up making sacrifices about like what inlining is allowed to do. So complicated and
Well,
hard. And
so I'm thinking like there is like a I could do like one optimization pass which is entirely local, just do like essentially O1, and then I could expose those already optimized versions as like the version to use for inlining for the other functions, and then do like a second pass on all the functions, which is like O2 plus these like already O1 optimized like functions. Or should I just like not do that maybe and like have the original version of the function available for inlining? And like, would that affect the optimization? Like, because I could see like how I could like significantly reduce the amount of data that I'm sending to like one of these translations if I like re-optimize them, because it also like tends to shrink the IR quite a bit.
yeah. Yeah, you probably should locally optimize them before you send them off to the, like, to the slaughterhouse. Have you looked into LTO? Because I think that ThinLTO might like do some of the things you're looking for, even if it's not like, the best.
Yeah, I think LTO maybe is something that I will consider, but like it's also like that strategy doesn't necessarily require much thinking on my part because it's going to take forever no matter what I do, right? Because link time optimization is just slow. But I'm trying to figure out how I can kind of get like assuming I haven't turned up the optimization to the max level, right? So I want to like figure out how I can get something to build very quickly, but also get like decent levels of optimizations from it. Like that's where I'm at, because like obviously if I just turn on like LTO, everything's gonna take forever, and then it's gonna write really good code. So what I'm not worried about that because that's straightforward. Just throw everything in one thing and then compile it all at once.
Well,
But it's like this.
ThinLTO is supposed to solve this scalability problem because it doesn't put everything in a single module straight away, but it uses some kind of module summaries that show what kind of facts can be exposed by each module. And then these summaries are used to decide whether the modules should be merged and optimized together. So it's kind of a middle ground.
Well, I guess the thing with ThinLTO though is that I'm just doing the ThinLTO thing with LLVM, and then I'm like here's the steps to do ThinLTO. You do the steps and then you're done. There's not really much like architectural decisions for me to make as far as even ThinLTO is concerned, to my understanding, right? Like it's like, yeah, throw the functions in ThinLTO and then LLVM does it all for you. I'm not really involved in that process in terms of like design, right? Whereas if I have this like incremental compilation where I'm like, okay, should I like pre-optimize these and then like inline them, and I'm choosing like which symbols are available in the like translation unit for inlining, then that's something that I have to decide.
What are you compiling?
Like functions and stuff. Like whatever code someone writes, I guess.
Well, what is the language and what kind of like I guess what is the scale, and then what kind of optimizations are you expecting?
Okay.
Like how important is inlining?
So this language is called Quaxlang, and it is most similar to C++, is the way I would describe it. It has some it's like a version of C++ where everything is statically linked. So you compile the runtime standard library, everything gets thrown in a folder, and then you're like, I want to compile this, and then it produces your binaries. That's the goal. Right now I don't have the LLVM backend finished, but I have the front end and the interpreter working. So it's not really meant to be an interpreted language, but I had to build one for const expr support. So
For the mode where you import functions into the module for inlining, this is very similar to what we do in Falcon. That's LLVM based Java JIT. We start with each compilation request is a top level method that the runtime asks to compile, but then we rely on inlining heavily. So we want to inline
yeah,
well and.
LLVM has something like inline function definition. So it's really like the choice of like what's it there's I forget what the keyword is, but anyway, there's a keyword that says, hey, don't emit this in the translation unit that or like the object file that you produce. This is just here for you to inline if you want to. So there's LLVM has this like way you can declare a function, say, you can use this for inlining, but don't actually produce this in the object file if you don't inline it.
Yeah, we don't even use that. So what we do is we have a custom inliner because LLVM inliner is bottom up, but we start with a single function in the module, so we don't have we cannot do bottom up. So we have custom inliner that does kind of top down exploration. Basically, for every call site, it decides I want to generate the IR for it, or in your case, it might be just grab it from the original module where it lives. And then it may decide to inline, may not decide to inline. After the inliner is done, we just drop everything that was included in the module just for inlining. I guess that's the attribute you're talking about. So this works. Our inliner sees everything it needs to see. However, it comes with a compile time cost. I think I had some estimates that maybe about 30% of our compile time is wasted on these like repeated generation of the same candidates, just handling them, and then maybe discarding them and not inlining. So it gives you better performance, but it comes with the compile time cost.
Well, I won't have to generate
I guess
something
not surprisingly.
multiple times because I would like save the like I would do an O1 pass and then cache that and then make that available for inlining. Like maybe there's some overhead in terms of like adding it to the module if LLVM does some internal duplication, but it's not going to like recompile it or re-optimize it like until it's like decides, okay, I'm going to actually use this for
Yeah,
inlining.
we don't have a cache for this, so we could save some of this cost by caching the inlining candidates. One thing you can do if you're willing to spend some compile time, once you import the function into the module, you can specialize it. Let's say you know it is used from a single call site, and you know this call site passes, I don't know, constant arguments. You can specialize your copy for constant arguments, run simplifications, see that it actually shrank and got smaller, and maybe this will trigger inlining, which you wouldn't otherwise do because you cannot see before you specialize and simplify.
Well, it sounds like
I
you do
feel
all
like
the work for inlining without actually doing the inlining.
I feel like LLVM would do the constant propagation already. Like if you, as long as you make it like I guess the choice is like, okay, I could, like when I want to have things that are inlineable, right? there's two options. One is I give every function that exists, and I say LLVM, these are all the functions that this function can reach potentially, and you can inline as far off into the universe as you want. You can inline every single function that exists into one thing if LLVM decides to do that, right? Maybe that's not what it would do, but like I could make all of those functions available as inline definitions. Or I could say, okay, I actually don't want to make I want to have some heuristic. I want to say, okay, you can, go up to 4 levels deep or something. Like what's a good heuristic for like deciding, like assuming I don't want to make every function available because I want to like this is the fast compilation pass. This is not the full optimization level 09, link time optimization, everything, all
Well,
that.
if you have this kind of exploration heuristic, it will basically limit your inlining.
Well, yeah,
if you say that you're exploring only up to 4 levels deep, it means your inliner is now only doing up to 4 levels deep. So what we ended up doing, for us, exploration is driven by the inliner pass. It goes top down, and if the inliner wants to look at the function, it will see it. We will generate it.
I'll add
So basically, we folded it into the inliner heuristic. If the inliner wants to explore a function, and it wants to do this, and like in most cases, it wants to see the IR.
So
Unless
do
it's
you
something
think
extremely
it's
cold.
not even worth doing this? It would be better just to like take every function and just throw all the IRs into a function and compile them all at once? Because like I could see this reducing like incremental compilation a little bit, like if I have to recompile everything together.
No, my suggestion is not to throw every function to the module. My suggestion, or at least that's what we did, and it's one of the options, is to do top-down generation driven by your inliner. But you'll need to have a custom inliner that does the exploration.
Yeah, I think that sounds like a great idea. So that's one option. One option is like custom inliner, sharing the heuristics. The other option that is simpler, but at your whatever warranty whatever is the ThinLTO option. It is not the most fast, but it is a pretty good option because it can do some parallelism. But the issue is that it is kind of having a like it tries to pick the better sacrifices, which is not like the worst answer. The best answer would just be that LLVM could be parallel, which is that's yeah.
I want to make sure that the inline decision depth of 4 is like way short for Java. Must be much greater than 4 for Java.
Yeah, that'll
Just-
that'll blow out like
which
basically
language is
everything.
that, and how sensitive it is to inlining.
I'm assuming it would be inlining sensitive as far as performance goes, but like I'm just trying to figure out if there's a better way to get, because like of course if my goal is as fast code as possible, which at the higher like optimization levels, that's what I want, then I'm gonna make everything available to the optimizer, right? But what I'm trying to do here is I'm trying to get the Go experience where you get a program that's fast enough at these lower optimization levels. You get something that's fast enough and it compiles quickly. And I'm trying to figure out what's the strategy to use to get that fast enough without where's the balance, like the right, I guess, balance point of like how much stuff I make available to the inliner.
Yeah,
Everyone's going to have a different definition.
It sounds kind of
another
like
simple
I
thing you can do
found
is
chemical definition for oxygen with nine oxygens in a row for the -09 question. Nonane, not hexane. I'll just stop while I'm behind. Sorry, carry on.
Yeah, so another option is you can view inlining. You can view that there are two types of inlining. One is canonicalizing inlining, where you inline stuff that's just there is no questions whether it should be inline. It's getters, setters, these kind of simple things. And then there is this optimizing inlining. That's where you come into this heuristics and trade-offs territory. So pick some definition of what is canonicalizing inlining for you. And then for functions that fit this definition, just clone them into every single module. That will give you like somewhat better performance and faster compile time.
Essentially,
I would basically split it up into like two phases. And by two phases, I mean two development phases. So one of them is do like actually maybe three. You could try that one. You could also try a ThinLTO, and then as a later stage, once you have like a corpus of like code and things like that, you can then try to like just stats it out and see if you can write your own inlining paths or maybe your own backend. You can kind of transition between those things.
Here's the thought though. Like if I make something available for inlining, right, and then I recompile the program, if anything that was available for inlining changed, then that also means all the things that were able to inline that function also have to be recompiled. Whereas if I have like, let's say I have a depth limit of 4 and some function that has a depth limit that would have been reachable at like 5 levels of recursion down changes the internal like implementation, but the interface doesn't change, then I don't have to recompile those functions because the I like it's not exposed. It's not an exposed detail, right? And like in C++, this would be based on header files, and like if the header file changes. In my language, there are no header files. Every function is equivalent, and there's no like, okay, this is in a header, this is not in a header. Like it's like a monolith essentially. So I have to make this decision.
I'm tackling the same problem with simple right now, where I throw into the object file the ahead of time compiled as you expect, plus the IR. But when one object file loads, he wants to get the header info from another object file, like from a Java class file, except it also has your ahead of time compiles. Having pulled in the header info from the other guy, that effectively lets him inline, and he chooses to do so or not. Then you change this guy over here, the guy who inline has to get rebuilt. I'm not putting a limit of 4 on, but I am putting a hook on this guy over here saying I depend on that. So if I've recompiled this, when I come back around the next touch I do on this guy, he says, I'm no good. I'm out of date. And I have to rid of this
basically dependency and invalidation mechanism.
I'm sorry?
Yeah.
It's dependency and invalidation mechanism. And I think it's if you need to do something like this, just build a generic dependency mechanism and not rely on this kind of 4-level deep. Just have a list of methods that you depend on and a list of methods that will invalidate your compilation.
It's also going to carry on to like the dependency graph needs to keep track of things like types, because even if the function doesn't change, if a type changes and the function uses the type, the source didn't change, but you still got to keep track of all those dependencies. So yeah.
Right, that much I can do pretty easily. I mean, that much I already have, right? Of like, I can check what the types are of a function, and then it would change its IR. But like the question is like, if I compile something, right, and then I recompile the program, and I have a similar compilation before, I have all these like cached definite, like here's the IR of the function, and then here's what it looks like when it is compiled. But that if that is using inlining information, that also depends on what those inline functions are. And like what I don't want in my like fast build mode is for me to change one function at some random point inside the program, and then that creates this giant cascade that basically recompiles everything in the project.
Well, wait, you got a fast build mode. Fast build means you didn't optimize, or you didn't inline, or you didn't something.
Well, it means that
I
want some level of like balance between like I want some inlining up to like some but I want a heuristic that cuts off the inlining in a deterministic way where I can say, okay, this function couldn't possibly have been inlined in this situation. So I can say, okay, if I change this function, then there's a limited set of possible functions that need to be recompiled. It's a finite number. Like it's not going to. It shouldn't force the entire, like if I recompile, if I modify like the right function, it shouldn't recompile like the entire program because everything eventually does IO somewhere. Like there should be some set of functions that get rebuilt.
This part is actually like doable. So imagine you have like a table that just says you've got your object files, and these are your final compiled output. Those things reference the dependency graph by saying what versions of the functions do we have in each object file. If you inline, then that version is in there. Even if it's indirect, it's still in there. And so if it changes, you want to do the lookup the other way, where you can say like, hey, for every single function, if any of these functions change, tell me what the dependencies are. And you build up this dependency graph that is separate from your original one. That is the grouping of just like inlined, of like the final output inline versions of the dependency graph. it might have duplicates. So if you edit the write function, maybe there's like 3 versions of it inline somewhere. So it's going to have 3 points. All those 3 points are different object files. You recompile each object file. And then separate to that, if you can build that, then the trick is that while you're building it, you can also then just set restrictions on it because you now know the list of things that need to be edited. If the list starts to get too big, you can just set a cutoff point. So be like, hey, I don't want to inline something so much that it would edit 5 object files, for instance. I mean, you could set the heuristics differently, but obviously what you can do is then you could say like, well, my dependency graph is getting too messy and I'm willing to sacrifice some quality as long as it keeps compile times reasonable.
I went down the path of saying I wanted to be deterministic as well, up until I started inlining, especially cross-module. So there is a thing there about you're going to get some arbitrary cutoffs that are based on potluck ordering of how you visited things and who edits what. Spinal Tap is to turn it up to 11. Yep.
Yeah.
I think you're well into the land of heuristics, sir, and it's whatever you want for heuristic.
So I'm hoping that it doesn't sound like we have a good heuristics for this yet. So far, it sounds like build an extension to LLVM that tells me something about it, and then
I mean, everyone has inlining heuristics. It's just the nature of the beast. And they're going to vary according to what.
Well, it's not even the question of like whether it's inlined. It's the question of like whether the details are exposed for inlining. Because if I expose them, then I potentially have to recompile because LLVM might change its decision if the definition.
Just said, I'm going to stop inlining because I didn't want to expose so many details 4 levels deep, 5 levels deep. So you have a heuristic that says inline 1, 2, 3, 4, stop.
Well, there's two heuristics. Like one heuristic is, do we actually inline it, which is going to look at the content of the function. The second heuristic is, do we make it available for making the decision to inline? And this is important because we have to distinguish these two cases for a deterministic build. Because if I say that something is potentially inlineable, and I say, okay, this is potentially inlineable, and I say yes, but it doesn't inline it, and I change that function's internals. Well, if something was potentially inlineable and I change the function internals, I still have to recompile its descendants because whether something would actually be inlined could change depending on the internals of something that's potentially inlineable. So you have this like question of potential inlineability, and then the actual decision of inlining is made by the back end.
You're hunting for a heuristic that says when do I inline and when do I don't.
No, I'm hunting for a heuristic which is like when is something potentially inlineable, and that is because
that's just inlining heuristic. It's just convoluted.
It's a different tier of it.
Heuristic.
Yeah.
No, it's important to distinguish them because if I
be, but there's still an inlining decision going on here.
Right, but the potential inlining is relevant when it comes to like incremental recompilation. Because if I have a function that needs to be recompiled, and the set even if a function,
there's a lot of ways to slice and dice. I want to be incrementally compiling or recompiling or inlining to recompile across compilation borders. And I'm not saying your heuristic is bad or good. I'm just saying acknowledge that there's a lot of ways to slice this guy. You're headed for a certain one. That's great. But it's not the only answer, and it's not the end of the world if you get it right or wrong.
Yeah. Well, I guess like what are it sounds like
you won't get it perfect. There is no perfect because it's an open-ended problem. So probably even halting problem. It's not even going to be exponential. It's going to be bad. So you're doing an approximation. Okay, within the acknowledgement that it's an approximation, make your life easier. Do whatever is easy.
Yeah, in early days in Falcon, we had this, when we still used LLVM inliner that did the bottom-up part, we had this kind of preparation pass that would do exploration first and then would pass it to LLVM inliner. It just messed with the inlining heuristics. It was difficult to reason about because, well, the inliner would like to inline this method, but the exploration pass didn't see that it's beneficial. So we ended up just replacing it with a single top-down inliner.
Hey, unrelated question to Arthur. Is Gil Tene still at Azul?
Yep.
Yeah, okay. I sent him an email the other day. I didn't get an answer. Poke him once. I want to say hi. Okay, that didn't mean to stop all conversation. Yes,
Yeah.
absolutely. You betcha. The chat is going to be very entertaining this go around. We should throw it on the. I'll see if I can get it thrown in with the YouTube channel. What are you saying about Aaron? About you couldn't inline anything that was not shared mutable state? Aaron. Now I'm blasting Aaron. You wrote something in the chat and you've gone offline. Darn it. Okay. What else? Are we done? This is like I stopped all conversation. Not certainly my intent.
Okay, let's come back to CF nodes and AST. We thought how they are alike, and let's talk about how they are different.
Oh well, yeah. That was the and Aaron's trying to do it in chat. We need you in voice, Aaron. It's slow going in chat. The CF nodes, the ASTs don't have common sub-expression elimination per se. The root of the tree doesn't share value. It doesn't share conveniently.
I was thinking that is any AST node is exactly source representable? It has to be something that it's in source. The CF nodes represents effects and something like that are not actually present, but are kind of alongside the source.
Yeah, there's not a mapping from CF nodes to the original source that's so convenient. Yeah. What are you asking about them?
No, I'm just thinking, is that actually a characteristic for the AST? Does any AST node has to be exactly source representative?
AST is just a tree. Do what you're going to do with it.
Yep.
The common things that comes from the tree of the source code, which itself is a nested BNF, so it's got a tree structure. You're just exposing the tree. It's a very straightforward translation. That's easy. Fine.
I would say that 80% of CF nodes are AST nodes. They have one-to-one mapping, minus the things that are memory effects and something like
merging
that.
Of one kind or another. You get a finer grain merging than in an AST. So if I have a series of if then else's in CF nodes, I can carry values between the different arms of the ifs kind of conveniently. And in a AST, you would typically say I have a block and it has a tree and then has another tree and another tree. And then crossing between the trees is less convenient in an AST there. Anytime you say a statement with a list of nested ASTs, that statement is kind of a border where things don't cross conveniently. You can cross them, it's just not convenient to cross them.
Yeah. And I would say in CF nodes, you have tools that are kind of delving into approximating program execution. You have some tools out there can kind of I don't know the exact words. They can kind of step into the program execution, and you can model that inside the CF node. So
it's the semantics of the program. Yeah.
Yes.
But so's ASTs, except they carry state from the end of one tree to the start of the next.
But they don't represent execution. They just represent the source as it's captured by.
They're very close. So
that's like that gets categorical.
Any program represents that something you're going to execute. That's lambda calculus, but turn that into Java and Ruby or whatever. Same. And then I got an AST. Of course, I can execute an AST. It's just that when I hit the end of one AST and I jump to the start of the next piece, like I said, I have a block with a pile of AST expressions, one after another. I have a series of trees. I'm going to go walk a tree and do it. And when I get done, I go walk the next tree. Well, I carry between each tree, commonly memory state, as a for instance, IO state, anything like that. And when I optimize, then I need to figure out how I'm carrying from tree to tree. And that's the part where it's less convenient. If you're instead saying, I'm trying to put something back to the user because I'm trying to do an IDE and show them the program after I mutate something, AST is way the hell more convenient because it has a mapping back to things. But for optimizers, it's less handy.
Yeah, you run into this annoying thing with if you have static analysis, you end up reconstructing basically your SSA pipeline, but again, and this time, like not technically optimizing, but totally technically optimizing because you're doing a bunch of data flow things to like expose facts about the program.
Yeah. Comes back around. And Max wants to talk about egraphs, which put a link in the chat, but I've seen egraphs before. Where'd it go?
No, not egraphs.
Egraphs.
So Chris Fallon wrote an interesting post about this acyclic egraph thing that ends up kind of looking like a half sea of nodes, where you have a skeleton or a spine or whatever it's called in the graph, and then all of your other sort of pure or non-effectful nodes float. And then you have to do some kind of elaboration to put them back when you're scheduling. And so you end up with like a lot of the canonicalization properties and hash consing and all this stuff still reasonably within a CFG pipeline. And it's kind of interesting because it fits nicely into an IGVN as well.
I'm taking a top level glance at it. I'd have to stare at what they're trying to accomplish that I'm not going to get out of my sea of nodes to figure out what they're excited about versus not excited about. This is for the crane left. This is Rust, right?
Yeah.
Somebody tell me that crane lift and Rust go hand in hand.
I mean, there is a crane lift is implemented in Rust. They've gotten their data structures really nice and small.
What is Rust? I thought crane lift was used to compile.
There is a backend for Rust now.
Yeah, it's a backend.
Yeah, is implemented in crane lift, but I think it's not landed yet.
It's basically what happened is that like for the last like 10 years, there's been the whole discussion of Rust compile times, and crane lift was kind of like touted as potentially being the saving grace, but crane lift had other interests like WASM and stuff.
Oh, I see.
Yeah. Okay. It's not that they couldn't be used for like Rust compiling, but that's not really what their priority was. Like their priority seemed to be, I believe, was it WASM time? Is that the one I'm thinking of?
I'm watching this guy talk
about
it's WASM time. Phase ordering problems. Give an example that Sea of Nodes completely solves directly in the obvious way. This feels me very similar to the last go around. Somebody said, and Sea of Nodes does this, and it doesn't. Fine. All right. I need to, oh God, it's going to be another ad hoc. And here we did. Okay. So that's a deeper read to make sense out of. Why did you want to talk about aegraphs? I'm not saying it's a good or bad, just asking.
Well, we're talking about CFG and we're talking about Sea of Nodes, and I think there's some interesting middle ground. I'm not going to be pivoting my compilers to Sea of Nodes soon. I think I every time I try and go walk through this simple tutorial, I get bitten by something or another, and I run out of time 4 hours in, and I'm like, okay, maybe I'll come back to this.
I would be very interested if you gave me feedback on especially what bites you, because
I think some of it is
you don't have to do it online right now. This is just I would like help in understanding how to explain what the hell is going on.
Well, it's not a lack of understanding exactly. I find that maybe it is a lack of understanding, but it's deeper. The wiring of stuff where you have to plumb your data dependencies and unlink them in the right order and this, that, and the other thing, very finicky for your sort of double your double linked nodes. So if you're optimizing a thing and then you end up deleting it, you have to, there's all these like big warnings in the comments that are like, if you don't do this in the right order, it like spin locks or whatever, or it like there's a null pointer exception or something. And I get stuck on breaking one of those things by accident, despite literally porting the code. And that's one of the reasons that I I'm a fan of the block parameter approach to things these days, is because it's a less linked version of phi's, where you're pushing arguments, and you just kind of, if you want to swap your block target, you just swap your block target, easy. And I don't know, maybe that's just me.
No, it's not I mean, it's a valid criticism. There is another choice. There are actually a couple of choices I went through. I've picked this one, but it's reasonable to argue, another variation of that, which is the block one that says I have one pointer where control comes from, and then I have a list of data values that come along at edges. The current phi situation means every phi carries a control edge. So I have a big pile of redundant edges there. That redundancy gives me simplicity elsewhere for complexity in another place. Complexity in manipulating the set of merging paths coming into a control block header in exchange for simplicity in how I compute values on a phi. Having said that, Derek Weeby, who's not here right now, went down the same path I originally did at grad school and wrote my early PhD thesis with, where I did something even more split out for how phis work now. It's not really a phi. It was done even simpler in a way. That gave me a lot more nodes in a graph with sort of simpler semantics, and it also detached the how you split control in and out separately. So there is some choices here about how you design where the control flow merging goes. I've picked one, but it's not the only way.
Yeah, I think in general, this is a trade-off that's with CF nodes, you have more, like your dependencies are more explicit. There is more stuff that you need to care about, but it gives you convenience in other places.
Yeah, right, exactly. And I don't know, depends on which way you're headed, which one is easier for you to understand and deal with. And then what do you say about the type system?
The type. So first, I haven't fully wrapped my head around the you have at least in C2, and I haven't poked at simple too much, but you have it's like either meet and dual or join and dual versus meet and join. And your argument is reasonable, which is it's really hard to implement both, the exact same way, and it's easier to
Dual is
implement
trivial
dual.
in any case.
Well, so I haven't fully wrapped my head around what's needed in your type system to have that symmetric through line. But so that's one thing, and that's just like a me thing, and I'll get there in, I don't know, 3 years when I eventually write a blog post about it or whatever. But that's how I learn. The other thing was there's some notion of computing types as values, which makes sense, but I couldn't wrap my head around when it was decided that something was a const. Like the lattice structure felt confusing to me some way. Like I don't know what it was. Like I have the same representation plus minus a couple things in my hobby compilers where it's like you have a bit set and you've got a thing that can represent a single object and you've got some other stuff. And I just completely bounced off some of the type compute, remove this node, don't remove this node, dedupe, whatever. And I don't know what it was. Maybe I'll do a live stream and I'll just it can point at timestamps of where I bang my head on the table.
Okay, yeah, I'd be curious because the actual lattice is straightforward. It's distributive, complete symmetric bounded. It has a few more buzzwords than the minimal lattice, but it's a straight up mathematical entity that's pretty simple.
No, I think it was not the lattice itself. That's fine.
Okay.
There's like the Java representation of it where it was like, what is going on? And something happened.
And I did a lot of things in the Java representation to remove redundancies in the Java code that makes the Java classes not one-to-one with the types.
Oh.
Does that make sense? So type integer, it's Java class to an integer lattice, it's one-to-one. That one's straight up. I wrap to have a mega top and a mega bottom. That's plain type. Within plain type, there's also control and X control, the dead control, and the yes or no control, reachable, not, however you want to do it. So plain type says I do all the simply structured types, which is yes, no, and control, and null or not the null. And there's one or two more. There's not too many. These are all choices, this or that. And because they're so trivial, they have no internal structure. They're essentially a bit that says I'm this way or that way. And then integer says I have the meta top bottom, but then I have this whole range of things. And then the floats have their own things. There's 32 and 64. They have a little bit more structure than just a yes, no, but not too much. They have a high 30, high 64, high 32 constants, low 32, low 64. So there's an extra step in the middle. Pointers want to get fancier because they want to say, I point to something, and then I'm null or not. And if I point to something, then I get a struct, which is a set of fields which have named and an entire type, whatever the whole type hierarchy could be. So they're recursive. Function pointers are like memory pointers in that they're null or not, but then they have a signature and a return. So there's a collection of types that are not named with names like type structs. They're just say ordered arg0, arg1, arg2, or the return. But within that layout of things, like type has this, hey, I handle all the simple types, and everyone else inherits from me. So I handle all the common behaviors like compute the dual and compute the meet. Compute an ISA from a dual and a meet things. Does that help at all?
Maybe. I mean,
there's a lattice, and then there's a Java implementation, and different parts of the lattice are implemented by different Java files, but there's not a one-to-one file to lattice element per se, because there's this common sharing thing where there's a couple simple guys that the basic type guy does.
Yeah.
Yeah, you don't sound too convinced, but that's fine because it's all whatever it's going to be, and it's hard to do it on the fly. I have these pictures.
Yeah, the pictures were nice. The pictures make a lot of sense, and the structure of the lattice makes sense. I'm just like looking at the Java files. I got a little.
Yeah. Blah 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 blah. Go back to Slack. Find share.
What is xmeet?
Find this. So I have here's the full blown, all singing, all dancing lattice. There's a lot of parts to it. But then let me.
I believe xmeet is just the inner version of the meet function that doesn't have some of the scaffolding around it, so it's called differently.
Yeah, hang on. Which one are we at here? Source mean Java type. Yes, yes. Nope. How about this? Yeah, Zoom wants to grab things. So somewhere up top, there's a type class. He says, this wild lattice is actually, go find things from Wikipedia. I'm a type. I have a bunch of maintenance jobs. Internally, I list like, here's all the different types I might have. Many of them don't belong here. Somewhere I say is simple as I'm done here, and here's the things. Top, bottom control, X control, null, anti-null. Okay, go back to my big picture. So if you can see my mouse, top is the black top, bottom is the black bottom. X controls the top control, upper left yellow, lower left yellow, bottom control. There's a null pointer, which is the guy in the middle, which you could be null or not the null, the little green pointer or question mark pointer at the bottom green. That's implemented in the one type class, along with all the sharing of things about how you compute lattice, a meet and join, and ISA tests and duals and things, printing functions and visiting functions and the like.
Do you overload the X prefix to mean different things in different areas? Like X control versus xmeet are like
unrelated. The X here for X control is unreachable. I could have two names, reachable and unreachable, instead of control and X control. Otherwise, X is a convenience thing. So go back to type here. X is a convenience thing that says this is an internal. Right.
Oh.
So publicly, the meet says, I'm the meet of two types. Do an initial assert that you've already interned things. If you're identical, done. If you're simply typed, so if you're identically typed, you're meeting two function pointers, you're meeting two structs, you're meeting two memory pointers. Go do a specific breakdown flavored meet, take a virtual call, do something. Okay, nil says, I am part of everything that's a pointer. So if you're a nil guy, then I do a convenience different meet. That's the meet for null and a function pointer, or null and a memory pointer. Otherwise, I'm simple. That means I'm implemented in this file and I have just a table lookup. Just go, I have X control meets nil. That's completely undefined. Go to bottom, you're dead. Whatever. That's a simple breakdown. Constant arrays kind of didn't fall into this pattern nicely, so they got an extra point here. I didn't like them there, but fine. But here, the main thing that happens is xmeet on generically things. So
What
xmeet,
is
if you're a
nmeet
simple
and
guy,
ymeet?
has a table lookup broken out as code. Otherwise, it's overloaded. And for instance, I would go to type integer and look up xmeet. And he says, oh,
Okay.
I'm integer. I'm guaranteed I'm unequal to myself, and I'm guaranteed I'm the same Java class type. I'm an integer type. So I just cast you based on contract. Then I do the meet. And the meet is for integer is math of the mins of the mins and the max of the maxes.
Okay, I think I got really stuck in the prefixes. Xmeet, nmeet, ymeet, meet.
Yeah,
X
ymeet
control
is
versus
I
control.
had another further breakdown of some common shared thing that was just structurally convenient. I needed another flavor. So what would you call xmeet here? It's the internal meet that's specific class to class. Floats to floats have one, type pointers to type pointers have one, type mem pointer.
I probably would have called it float meet or integer meet specifically, but
So that
I
would
don't do virtual
require me,
dispatch in mine.
that would require me to have, like, this is a virtual call right here, xmeet. That virtual call, it's a virtual call. It breaks down into 10 different cases. What name do I
Yeah,
give that virtual call?
internal meet. I don't know.
Yeah, it could be.
We have
Okay.
slightly different naming styles, I think, or naming philosophies,
Yeah.
which we've explored over email as well with
Yeah, it could
array
be.
versus RE.
This could be done as internal meet. I would use impl, IMPL for that, but I could have had
That
this
works too.
xmeet meet impl. And then
All right.
often the case for meets is they're recursive. They have internal structure. So this meet says, do something about null or not. That's the meet zero. Object
Oh
meet is
no,
totally recursive.
what's R dual?
Okay, so now I get into, this is where it gets fancy, and it has a brief discussion and needs a much deeper one. X dual is the easy one. It says, I'm the dual. I just negate all my pieces parts. Recursively in case of here, or just do a bang on the one for the guy that says I'm a constant, I'm a singleton memory pointer or not. R dual says I am representing a recursive structure that loops back to itself. It's a cycle in the types, and I'm interning them. And the issue with interning cycles is that you can present the cycle in any piece of the cycle first to the type system, and the internal representation has to match the cycle however it's rotated and say, oh, you are the same type. So I have types that can be cyclic. So linked list is a classic case. A linked list has a next pointer, which is null or points to a linked list. That's a cycle in the type system. I put it as a cycle in the Java object representation for a linked list. And you get a type memory pointer points to a type struct, which has a next field, which points to a type memory pointer. And it's the type cycle. That makes a bunch of other things very convenient and makes me completely, when I'm outside the type system, makes me completely not care what the types do. They have all the properties I care about them, including if A points to B, points to C, points to A, all that just works out as standard lattice theory. It's, symmetric, blah, 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 bounded, limited, bound, distributed, all that kind of stuff. So it's very convenient outside. Inside, when I have cycles like that, I need a way to represent the cycle. If I look at classic compiler implementations which do cycles, like linked list has a next field which points to a linked list, they break the cycle by having the guy that's some guy at the bottom or the top, however you want to think about it, is accessed not by just chasing pointers through the type fields, but by saying, oh, I have a symbol. I look up the symbol in the hash table. And here I have gotten rid of the hash table. I just say, if I have an A type, here's all its fields. And if I have a field that has a type that happens to be a B type, it points to its fields directly. It's just pointer chasing. So the end result here is I want to represent cycles. C2 does this as well. The implementation means I have to intern cyclic things, which means I have to take a wad of something, some type I'm trying to build by parsing user text, and I build it piecemeal parts, recursive descent, which means it never found the first piece because you're recursive descending, so you haven't finished the first piece when you went to the bottom and you discover it again. So you build a non-closed type. It's not interned. The interning says, hey, go discover the cycle's closed. Great. Look up in the hash table, see if I got a hit in my cycle. If I do, or if I don't. And if I don't, I'm going to intern you. I have the intern piece already. I'm going to do the duels. Our duel is specifically make a recursive duel at the point where I have discovered I have a closed cycle and it's new, never seen before, intern it.
That sounds very complicated.
It's simple in mental space when you use it. It's complicated to set up. The mental space model is I asked for a type generally by mixing two other types together with a meet or doing an add on integers or whatever. And I just say, give me a new type based on the old types. And the types all have the property that from a type, I generally, if it's recursive anyway, I can just chase pointers to get the next piece. I don't stop at a hash table and say, it's a symbol. The symbol references the root linked list piece.
Yeah, it's all internally linked.
It's all internally linked. Yeah. That's all that it's doing in that sense. It's very contained within the type system itself. From people who consume the type system on the outside, don't care. And it doesn't happen until you get to structures, which can have these cycles. Up till chapter 20 now, 18 or something, you can't make a cyclic type. So it never happens for a long time. If you go back to earlier chapters, this never shows. And in fact, it's not implemented until later chapters.
Well, that makes sense, I guess. We have a much different concern for a type system, which is we just want to be able to do type unions cheaply, and we don't have structures because they don't exist in the same sense as in Java, because everything is shape-based or inline, or whatever you call it.
Yeah. I do cheap
we don't
unions.
do function pointers.
I have cheap unions here, definitely.
How do you do cheap unions?
Well, that's meet. Meet almost always looks like compare two sets of bits and them or them. Recursive, okay, and some bits. Then throw it in the interning. That's this guy who said, go give me a blank template of a type pointer, stuff the first Boolean, recursive the meet, stuff the second Boolean, hash it in the hash table. I get a hit 99% of the time. There's a huge hit rate on these things. And I'm done. And then throw the thing back in the free list. It never left L1 cache. It was like the recursive call to object, which is a little more complicated. And otherwise, there's a couple bit tests and some field sets, and you hash the thing, and then you looked up. You got a hit.
Do you intern classes and assign them bits or something like that?
The classes are type structs or classes. So yes,
Gotcha.
they're interned identically. A struct is just another class. Or a class is just another struct, maybe. There's like, and actually in simple, and in C2, it is just, the struct is the class is the struct, same thing. There's instances,
What do you do?
And then there's a class, like in simple and in C2, there's the notion of the class struct class, and then there's an instance, a particular instance. If I say new point, stuff a 2 and a 3, I get a type struct whose class is point and whose X and Y fields contain constant 2, constant 3 as a Java type, as a type thing in the type lattice. And I can go back to my type lattice structure and point you where in the lattice that structure exists. So it's an entity in the lattice as a type. It's a Java object as a Java object that has a type struct that has a 2 and a 3 in the X and Y. Okay.
What do
I
you
also
do if
have
someone makes
class
like
point.
1,000? Yeah.
Yeah, yes, you might get some count of them. In the land of C2, run over 20 odd years, I discover that there's a corpus of about several hundreds of types that are common for everybody hits. Any individual compilation typically hits maybe 1,000 more, maybe a couple thousand, and then no more. The fact that you could constant propagate a point object with 2 and a 3 doesn't typically happen though, so you don't get bajillions of them. You get a handful of specialty cases, and immediately it turns into constant propagation. They collapse, and the code folds up, and it goes away, and you don't care anymore. But the actual count of unique objects in compiling any large Java method, unique class objects show up in the class and turning table is on the order of thousands, not on the order of millions, and not even the order of 100,000 or
Do you just have
10,000,
a big bit set
thousands.
or something? Because we only have it
Sorry?
in like a U60. We pack everything into a U64, and then, I don't know. We haven't thought
Yeah.
about giving it more bits.
C2 does things more optimized. Simple does things more in your face to be more obvious. Somewhere up here, I say, I have the singleton bit. It's not a packed long anything. I have a nested type struct separate from the pointer, so I can track null versus pointing to a thing, but maybe you could argue simpler left or right. I don't care. Structs are, again, not as simple as they could be, or not as compactly represented for performance as they could be. They're represented in the most obvious way. It's an array of fields. And then the array itself has a field, which is a name and a nested type, and is it final or is it whatever? There's no optimization there. It's just this is the plain obvious thing you would implement. And then practice says I don't get bajillions of them, even though I can be completely precise down to every nested field. If you make an array or make a linked list of length in a row without using a loop, and you put different things in each field, I will precisely represent that type directly in the lattice, directly as elements in lattice and then Java objects. So if you say think list point to this, da, 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 and then you unwind those, he'll unwind it perfectly. You dumbed it in, pull a thing out, he'll have it all. You get approximations at loops, which is what everyone does when they write code, so you don't typically see bajillions of these things.
I like the idea of the local intern bit cache thing. We might just add another field for we're probably not seeing more than 50 different classes in a method, so.
Right, same. I have classes as just another type struct, and then I have particular struct instances where I know something special about the fields that make new unique types, including classes that are class in the Java world, or point instances where I might know something unique. Usually I will say a point like you're talking about would have two bottom ends, two basic. I don't know what the ends are. But if I've just constructed it, it's brand new, and I jam my 2 and a 3 and it hasn't escaped, I have that type. It's the point of 2 and 3.
I think we probably represent that differently in our. We'll get escape analysis in the next 5 years or so.
There you go.
Then we'll do something.
It's not escape analysis here in any way. It's just.
Well, if you represent a point containing 2 and 3,
yeah,
that's pretty specific. Oh, actually, sorry. This is why. You're talking about Java int 2 and 3, right? We
yes.
don't have that. We have everything's objects.
Yeah, you have a different problem there. Right. But when I talk about it's the point 2 and 3, what I meant is that you wrote the code new point 2 comma 3 just directly, right? And then under the hood, there's a new init function which says, this came down to whatever malloc came from, and then pointer, and then pointer.x equals 2 and pointer.y equals 3. That's the sort of inline of the constructor. This code in the IR says, malloc says, I made a new type struct. That's the type. It comes from every node in the graph gets a type. This is type struct. with X set to bot or top, actually, because it's not initialized, and I do track that. That's a type. So if I go in my type constructor, I can say, make me type struct. It has two fields, X and Y with top and top. That'll happen. This will just replace the one with the other, with the two will show up. I'm just saying it's inline code. There's no escape analysis here. This is like inlining code here. That's because this is a store op, the pointer x equals 2, who takes as his input address the prior memory, the prior pointer made from malloc, and his memory state from the malloc's private memory. So this guy here made me a pointer to this. So it's a type MP pointer wrapped around it. And then there is a type mem, which has the private flag on it, because I haven't escaped you yet. And then it's a type S, type struct in memory with the top on the top, which is exactly the prior guy. So it's just shared. There's no allocation there. That's just the private memory wrap. Then the pointer here, the store op, this is actually a store node, which is what Yasser was writing. And he takes the pointer and the private memory and I don't know, something, the value which is 2. And he produces out this private memory pointer of this guy, and the next guy does the next thing, and you get the 2, 3 again, and it's all private because it's all in a row from a new allocation. There's no escape analysis here other than I made a private memory. If instead I went to a place where I had a call that said I take a point and I hack it, so I have some function header here which is hack the code. He takes a pointer, and under the hood he says p.x equals 2. The original memory he comes in with is already bottom point. He says, I don't know what this point is. It's a point where X is, bottom int. Call it just plain int. And Y is plain int. And when I hack it, I get a plain int. So I get the same type right back after I do that store. I lost it. And no new types though. And no sudden exciting new precision. And if this above code called it and passed that pointer along, because the function isn't inline in my little example here, he'd lose it. He'd say, oh, you escaped. I give up. Also, I don't know what the contents are. I give up. So the output of function hack is the alias fields for X and Y on the point have been reverted to the standard alias. I lost the private flag. It's all bottom ends. I'm done.
I mean, here's why I said escape analysis is because in like a Ruby or a JavaScript or a Python, everything just, it really, until you delete all of it, escapes immediately. Like,
yeah, I totally believe it. I totally believe it. So for me, I as soon as you have a function call, I've lost it. If I inline that function, I'll regain it in this case here. So it's not permanently lost. It's just, it's lost because the call did it.
Yeah.
In the land of the IR node, there's a call node here. And he takes a bunch of arguments, including that I'm calling this function hack. But I can look at the call arguments and say, oh, I know what function hack is. And then I might choose to inline it because it's a trivial function of small length. And I'll just like copy the code, get a private version, slap it down. Now, when I align the objects, they have a lot of redundant ones for the call and the function header that are cloned. They're all turned into no ops. They disappear. I get directly back to the IR that says, this will inline to nothing. And I'll recover my aliasing because I didn't have any nodes left over that to nothing. I can't type today and talk at the same time. And so
if you have a fee inside of PFX.
Yeah, the function header here, the implementation has a fun node. He has a parm, which is a fee, parm for P, and a parm for memory, and a parm for whatever, a couple different parms. He has a parameter P here as a parm. So this P.x, that's a store.
Yeah, but if you have a if something, then PFX is 2, then else PFX something different. You have to.
Oh yeah, if there's an if in here, you get more of it. Just so it Yasser's test case, right? If random.
Yeah, PFX.
Then my store node for 2, but it might have an else here.
Yeah.
Where P.x equals 99.
Yeah. Your for 2.
I'm sorry, then there's a fee for memory. that takes the contents of memory, the point, and would observe that he got a merge of 2 to 99 on the X field here, and Y is whatever Y is. So he would claim that this is true, except that I don't know what the memory state of except this pointer P is not private, so he'd actually not actually have this. He would say, give it up. I say buy in. Yeah.
Sure.
This is also a fee, the prom, because he takes arguments from all callers. And he merges all the callers. And in the land of not finished linking, that includes the mystery unknown caller that the linker will eventually call me with, which always takes all default arguments in the worst case scenario, and I get nothing. So if this function escapes into the outside universe, I have to assume an arbitrary caller comes with an arbitrary arg, and I get nothing. If internally I know that it's private, which I use an underscore in leading, but you could say private, and he didn't escape because you didn't take the address of the function hack and passed it around, then he would not have the arbitrary caller, and he would have the actual specific callers. Then he might sharpen point P to something more specific. But these are all, it's whatever the IR has the conservative correct case to begin with, and then I start discovering facts as I go along, and I sharpen it as I go. Typically with p-poles to sharpen.
You mean if function hack is called with a known point and points with the constant arguments?
It's called right here.
Yeah.
Right here. So I'll have here and this is the definition for the name. But the fun node will merge as series of inputs the call node up above. So I need a line number here. So I have a return program counter, RPC, straight out of an Intel RPC. It's your program counter return. This call node gets an RPC that's unique to it, RPC 1. And every call gets its own unique RPC. This guy knows that call comes from RPC 1. And he might have some other calls, or he might not. But I count them exactly. I build a precise call graph lazily over time. When I hit the parser, it's still approximate. I don't know that I haven't got the external escaped caller. So there becomes the default bad caller also. When I run through the opto pass, the optimistic slice of things, I assume nobody escapes, and then I prove that nobody escapes. And then that path goes dead. I typically now have a list of precise callers. And then I'll merge the inputs from the precise callers, which might tell me something about function hack is only called with people whose pointers.x field is only ever 2, for instance. More realistically, you could be told that he's only ever called with people whose parameters are not null, or always null, or something. You might learn something about null pointers getting passed in. And that's without any language. This is just what you call it, CFA 0 or something. It's the no cloning, least amount of effort interprocedural analysis. And I'm doing it with peepholes on the standard IR without any interprocedural anything. It just falls out in the wash. This is both C2 and no, that's not fair. C2 just inlines and he's done. He has the support for this, but he just turns around and inlines and goes away. But simple definitely does this.
Cool.
There's a lot of things here, right, that I haven't had time to put in the docs and write up, and I haven't had feedback. So I'm kind of trying to stabilize separate compilation simple, and then I was going to go back over with AI, see if I can clean up the tutorial some. Places where Max was looking at types going, what the hell's xmeet? Well, that's me just saying implemeet, meet impl, whatever. Whatever name you like internally, xmeet's not a great name. So in my view, there's a better version there.
Once you know what X means, then it's fine.
Right, but I don't. It's a coding convention. I have it written in the docs. Hey, when I say xmeet here, it's just a dumbass implementation meet that's virtual call to the 10 different callers. It's not even 10. It's like 5.
It's the specific implementation for the meet.
Right. There's a top level meet that does the easy hack. You're identical. You're the same class things. So I'm meeting two Java class things of the same type. You're both simple guys. I'll do the table lookup with the switch statement. You're both null pointers and pointer related. Then I'm going to do another, whatever. There's like 3-4 flavored things he takes care of that everyone deals with, or not everyone on pointers, but most people deal with. Then he says, I get up, call the medium hole. Okay, now if your floating point or your integer meet, you're meeting two ints. They're guaranteed two ints. And then now you do something sensible with two ints. Oh, I do the range thing, the ints. Okay, whatever. All right. It's time. I have a busy day today. I have a lot of things I need to do. So I'm going to go run. And I see Matt put something in the chat, and I'm just not going to get to it today, Matt. Feel free. What egg log saturation? Squeeze the egg. Matt Mole, something. Next next week, Matt. And then Max, I do appreciate feedback on simple, especially for readability for people. If you stalled out and you can remember where you stall out, why you stall anything, just send me a mail. It's easier than me trying to remember what hell happened online here.
That makes sense.
And I'll do something about it.
Next time I go around on my, because I blog about a lot of things. I want at some point blog about sea of nodes in the same style, like what is the minimal sea of nodes? And simple does not quite feel like the minimal sea of nodes. It feels like you can do a half size where you're not trying to do like everything from C2 at once.
Simple includes the ability to have function calls and structures and pointers. If you go up through simple through, I want to say chapters 6, 7, 8, you use pretty minimal. But then you don't have cool features. Like you kind of want pointers and structs.
No, but I'm saying the type system could be dumber. Like, or you could do whatever, or like there's stuff that could be shrunk to get at the core of this is the use def use, this is the peephole, this is the
The earlier versions of simple definitely have simpler things. Like the def use def edges, they have a very simple set of hacky functions that do the graph edge. You use these functions, your graph edges are taken care of. You don't have to think about it. And they do the obvious thing. I point from here to here. I want to change it to point to there. I decrement the use. I add the def, and done. There's a linked list hack. Okay. As I go down toward the more complicated things at the end of the universe, where I code gen the register allocator, and I will have to insert in certain places because I have ordering properties to preserve the allocation. I'm now out of a sea of nodes, and I'm both simultaneously sea of nodes and a list of basic blocks. So the basic blocks have a list of instructions. The edge manipulation hack gets more complicated. Fine, it does, but that's separate. And I could actually probably put those utilities in another function, keep the node class simpler. That's not a bad way to write it.
I haven't even looked at the code gen stuff. I have no internal good concept of like what reasonable, like maintainable and also efficient code gen looks like at this point. I've seen a lot of stuff and it is all bad.
Yeah, well, go write some code gen and go maintain it for a while, and then you'll.
Well, I don't think I can do it. I'm just saying I don't know. I've seen you look at all the major compilers and you're like, oh no.
Right. I claim that I'm fairly simple. I could reorganize to move some of the more complicated bits out of the core because the core doesn't need it. Yeah, Zaki says just back in. It's just ugly. And it's true. There's some stuff that's just ugly because the x86 processor is just ugly.
Sure.
So that stuff could be pulled out of the core simple. You want those support utilities, but only for the backend. For the ones I was talking about for edge hacking for the backend. The type system, I claim, is fairly simple. There are some complications going on. But the whole simple types, what I call the simple types, the control X, control, top, bottom, nil, not the nil, those are just a bit. The interning is the hack that is a performance hack, and it adds volume, a lot of volume to the code without adding any semantic meaning to types, except the implementation means if you have two types, if they're pointer equals, they're equals. If they're pointer unequals, they are definitely unequals. That question shows up so often that it's worth interning.
Yeah.
And that's the reason you have the interning. And can I say, here is a Java description of the type, and here's the interning logic in a separate file? Probably. That's a
It's just we
cleanup.
have ours in value types, so it's like we only have 128 bits, and they're all just if they're identical, but they're identical by construction, and if they're not, then they're not like
Right.
the two bits are different. Okay,
Right.
and so the pointer of it all adds a layer there. I wonder what it would look like if you used like the new value type stuff or value class stuff.
Right. Well, I took the indirection to make it obvious how it works. The value classes would subtract the indirection implementation wise. And so you could wrap your head around, I'm just looking at this wad of bits and saying they're identical. So if you skip the cyclic types, you don't go down the cyclic type path. Ultimately, it's recursive descent, a pile of pointers to pointers to pointers, and they're sharing, so there's a DAG. But any individual point in the DAG is just a wad of bits. Everyone has an equals function that says, check all my bits. That equals function, if you had squanched yourself down to a long or 64 128 bits, would just have been grab these 120 bits and equal or not done. That would be the identical where you're talking about now. I got structs, and you said you do not, although I would claim I would do JavaScript, not JRuby, but JavaScript with structs too. But I have structs. Structs add another layer because they have field names, and field names don't fit in 128 bits conveniently, so you kind of want to think about them. They have recursive types.
Yeah. I'll get back to you. I want to just see if there's something that fits in a nice 500 line file for like a minimal.
Yeah, absolutely.
Go
grab. Here, let's look at what did I do for chapter 1 on types. I probably didn't hardly nothing at all.
I'm not even complaining. I mean, now that I understand the different X prefixes mean different things like that.
Yeah, there are no types in chapter 1. That didn't help me at all. They might not show up in chapter 4. Oh, here we are. I got a base and an integer. And here's the base. Big old comments. Someday I'll do something. I have a top and a bottom. I have a limit count to the tops and bottoms, the simple types. I have an integer. That's it. I had some tests to say I exist. I made the bottom. I didn't bother making the top. I have a print. Done. And then life got more complicated. Now the ints also probably did something really simple here. I'm a constant. There is no ranges. So I made one constant, 0 for all time. There's no interning going on here either, right? So there's an equals
test. If you did known bits, what would the dual of a known bits be?
Same. Self dual.
Self dual.
Yeah. X dual. If min is equal to max, you're this. That's your self dual right there. Otherwise, you do something funny. You malloc a new type whose type is the min and the max reversed. It's weird for int, but it works well.
All right, I'll get back to you with like a 500 line thing, and we'll
Absolutely.
see.
I would love to see it. Yeah.
Well, I got to relearn Java for this. It's been 12 years.
Wow. Okay. Let me go throw this in the docs. All right, now I badly want to call it. I'm going to be tight here. Where I lost the window with types. Oh, there it is. Bam, threw it in the docs. Save, edit. Okay, then we're done. Entertaining, as always. And thank you, Max, for making this even more entertaining. And hope to see everyone next week. All right, bye-bye.
Bye.